Welcome to my Physics 2212 Lab 3 presentation. The purpose of this lab is to study distance dependence of magnetic fields due to a small bar magnet. The materials that we'll be using in this lab are a smartphone, a bar magnet, and 2 rulers. And the physics principles we are studying are the Biot-Savart law, which is shown on the right, and the distance dependence formula, which is equal to the magnitude of the bar magnet. The magnitude of the magnetic field of the bar magnet equals K, a constant, R, a distance, raised to an n power, which we will be finding in this lab. The first part of the procedure involves downloading the Teslameter app. And once you download the app, you orient the phone to where B of x is equal to 0, making it face the North Pole. Once you've found the North Pole, once you have pointed towards the North Pole, place a ruler along the east-west axis and place the magnet on one end of the ruler. Adjust the phone up and down, and then turn it clockwise, move it up and down again to find the maximum y and x and y value to determine the location of the magnetometer chip. Mark the location with a piece of tape, and the top right corner of the tape should be the location of the magnetometer chip. Adjust the magnet to find where the magnetic field in the x direction equals 20, 70, 120, 170, 220 microteslas, and record the distance between the magnet and magnetometer chip at those points. In the second part of the lab, you start by finding the distance that makes the net magnetic field equal to 100 microteslas and label it d underscore perpendicular. Then you record the y component at that point as b of earth. Add a second ruler perpendicular to the first ruler and move the phone up a distance of d underscore perp. Record the magnetic field in the x, y, and z direction at that point. And to find b corrected, you have to subtract b of earth and by b of y and enter it into the spreadsheet. And then the spreadsheet calculates b net at all those locations, which we will be using in the future to compare our data to see if it's accurate. And some observations we made during the lab were that when the magnetometer chip is far away from the magnet, it measures a near zero magnetic field in the x direction, if it gets far enough away. And as the magnetometer moves closer to the magnet, the measured x component of the magnetic field increases. And here is our Excel spreadsheet of the data that we found. We started with finding 20 micrometers in the x direction and measured the distance and the magnitude of the x that was given. And we plotted the data of the logarithmic function of b of x versus the logarithm, the natural log of r. And with that, we found a slope and a x-intercept we'll be using in the next part in our calculations. And so using them in our calculations, we used the B-bar equation and the Biot-Savart law. And in our experiment, we found the n to be equal to negative 3.34, which is the slope of the graph. And the expected n of the graph is negative 3, as we have seen in the Biot-Savart equation right here. Generally, it is expected to be negative 3, and so we were not that far off. And so to find k, the value of k, we would have to natural log k. We set ln of k equal to the y-intercept, and we solved for k at that point, which we found k to be equal to 0.539. And using that value of k, we were able to find mu and use it in our code to find the position of each and the magnitude of force of each arrow that we will be seeing right about now. So using everything that we learned from the previous slide, we were able to find the the magnetic field in each direction. And as we can see, it is accurate to our representation of a magnetic field that we learned in class, as the perpendicular distances are half the size of the parallel magnetic field, and they are pointing in opposite directions, and we have this accurate representation in the top right corner of the magnetic field in that location as well. And some assumptions that we had made during the lab were that other objects nearby had no magnetic field interference, and that the magnometer app was accurate. And we had to make estimated guesses with the app because the values were constantly changing when it was still. And some additional questions that were asked was, what if you hadn't oriented your experiment to compensate for the magnetic north and had instead laid out your meter stick at some intermediate angle with respect to the Earth's magnetic field? How would your results have changed? So the Bx and By values would be skewed by a constant. And the By values would not change that much, but the Bx value would, because we started at the point of 0, and then we moved it. If we moved it at an angle, then it would start with the starting value. So most of the calculations of B of x would be significantly larger. And what if you were to stick two identical magnets together end to end and run the experiment again? How would you expect your measurements to differ? So the direction of force would stay the same, or the direction of the magnetic field would still stay the same. However, the magnitude would be almost double of what it previously was, and the magnitude of the magnetic force would increase, and the measured distance would also decrease since there is a stronger magnetic force. And that is all. Thank you.